Thank you, Mr. Sherman, and all the attendees. My name is Daniel from the Polytechnic School of the University of Sao Paulo, and this research entitled Centralized Power Generation with Carbon Capture on the Commission of Short Petroleum Platform is co-authored along with Ronaldo Freire, Julio Augusto da Silva, Ciro Albuquerque, and Silvio Oliveira Jr. The main motivation of this research work relies on the underexplored opportunity for supplying the utilities required by a set of offshore floating production, storage, and offloading unit (FPSO) by using more efficient and environmentally friendly concepts of combined heat and power generation. Notwithstanding, there are stringent conflicting targets and restrictions on board that have ever hampered the allocation of those advanced technologies, in lieu of the business as usual layout, generally based on simple cycles gas turbines. Among those restrictions, weight, space, and cost are intrinsic to floating offshore petroleum production platforms. Thus, in this work, a techno-economic analysis of a centralized power generation system without and with carbon capture units is addressed in order to quantify the space and the weight allowance and the cost of those systems when installed on a deck of a decommissioned FPSO. Finally, the influence of the entrance in operation on the peak of power demand is also briefly discussed. A typical productive FPSO is composed of different operation units responsible for heating and separating the petroleum into oil, gas, and water. Produced water can be treated and discarded to the sea. A large amount of oil can be stored before a shuttle tanker transported to shore. About 150,000 barrels of oil can be produced, and up to 6 million standard cubic meters of gas per day can be either injected or further processed to be exported to shore via pipelines. Some other characteristics such as light weight and loading, as well as the hull dimensions, are shown in this slide. This data is important to verify if the newly installed components of the centralized power generation unit or power hub comply with the space allowance and the weight budget. In a standalone FPSO, the power and heating requirements must be satisfied by a set of four simple cycle gas turbines with waste heat recovery units. A large amount of heat is needed for separating the petroleum into its phases, whereas power is mainly consumed in compressors and pumping systems. However, in this study, the power hub proposed aims to supply the electricity required by four identical productive FPSOs. Notably, the demand profile may vary sharply due to the change in the petroleum flow and composition, rendering the determination of the most appropriate technologies and their load distribution on the hub a cumbersome task, especially when energy-intensive carbon abatement technologies are envisaged. To this end, four types of combined cycles are defined as modular power units. In other words, an MPU is each one of the several cycles that can be later combined in parallel with others of its kind in order to contribute to the overall power hub capacity. All the modular power units are composed of one LM6000 PC gas turbine package, a waste heat recovery steam generator with duct burner, and one condensing or condensing extraction steam turbine. Actually, the only difference between those MPUs is the choice between one or two levels of superheated steam pressure and the absence or existence of a CCS unit. For the sake of simplicity, only the layouts with a CCS unit are shown. The chemical absorption-based carbon capture unit consumes low-pressure steam, either extracted from the turbine or partially produced in the heat recovery steam generator. The full load operation efficiencies of the MPUs have been optimized considering the steam temperature and pressure as well as the steam extraction rate to the CCS unit as optimization variables. In this study, the objective function has been defined by using a weighted single objective function in terms of the efficiency aimed to be maximized and the cost, area, and weight of the hub top size aimed to be minimized. After selecting the most appropriate full load configuration, enough design analysis of each combiner cycle has been performed by using GT Master Suite in Thermoflow software. The acid gas package in Aspen HYSYS has been used to build and validate a surrogate model used to characterize the performance of the carbon capture unit. After the first part of the optimization procedure is achieved, consisting of the optimization of the process parameters of each MPU operating at full load, a second optimization routine is used to determine the minimum number of parallel modular power units that must be installed in the hub, depending on the peak and the lowermost demands. This later calculated from the sum of the extreme power demands of all the productive FPSO over the time. On the other hand, since the steam consumption in the CCS unit depends on the overall hub emissions, and those emissions in turn depend on the performance of each MPU when operating at partial load, an iterative process is required to determine the net power generated after discounting the consumption in the carbon capture unit. It is worthy to remind that only the one kind of MPU has been combined in parallel in the hub. After the MPU number of parallel MPUs is determined, an optimization problem of load distribution is solved to obtain the so-called sawtooth plot, characteristic to each hub setup, whose results will be discussed next. This solution process has been possible linking Excel, MATLAB, and ThermoFlow interfaces. In this 3D plot are shown the full load optimization results, or Pareto fronts, of each one of the four types of APUs studied. The axes correspond to the specific cost, specific weight, and efficiency. Specific area is not shown. Projections are also plotted for the sake of clarity. Strikingly, the specific cost of the carbon abatement technology drastically affects the economics of the combined cycle study. In fact, the capital expenditure of the power cycles equipped with a CCS unit could be almost threefold that of the power cycles without carbon abatement technologies. Here we summarize some of the results of the minimum number of MPUs installed and the net power hub electricity available after discounting the power demand of the CCS unit. Other data, such as the specific cost of the configuration selected among the Pareto front, is also reported. Regarding the defined targets, the power hubs equipped with CCS units are expectedly costlier and bulkier, although seemingly none of the power hub setups fall short of space as it can be seen in this preliminary arrangement below. Actually, depending on a scenario of carbon taxation, the financial drawbacks of the FPSOs with CCS units may be eventually countervailed. Carbon taxation scenarios will be part of a subsequent work to be presented soon in a dedicated oil and gas conference. Regarding the structural and stability issues, some previous concepts aiming to generate electricity for offshore platforms or aim to decarbonize electricity consumed onshore have proposed the location of the absorption columns in the lower compartments of the floating concepts. This will be also our case since the tanks for oil storage are no longer necessary. As it concerns the optimization of the partial load distribution, the so-called sawtooth profile can be used to determine the highest obtainable electricity generation efficiency for a wide range of electricity demands. In other words, this plot highlights the convenience for separately turning on or off and strategically derating a certain amount of modular power units operating in parallel in order to attain the lowest fuel consumption and less idle equipment, whereas complying with the environmental regulation. For instance, based on the overall power demand required by four identical productive FPSO without any delay of entrance in operation, the SATU plot previously shown can be used to determine the yearly and the mean power hub efficiency over the project lifespan. As it can be seen, for the setups without CCS unit, when two pressure levels of steam generation are considered, the average electricity generation efficiency of the power hub is not much different from the case in which single pressure level is adopted. This trend is less evident in the case of the hubs equipped with CCS unit. This fact suggests, at least for the powerhouse with carbon capture units, that simpler and more compact bottoming cycles may be favored over bulkier and costlier reheating of feed-water heating components, justified by lower costs of weight. Meanwhile, it's true that the overall efficiency of the hubs with CCS units almost 8 percentage points higher compared to that of the CCS-based ones, but only at the expense of tenfold more CO2 emissions. If we consider the effect of the delay of entrance in operation of the four productive FPSO, some interesting outcomes could be obtained. For instance, if the delay of entrance is set at 6 years between one FPSO and the next, the peak of the overall power demand to the hub may drop up to 30%, reducing the time that the MPU operates at partial load. Furthermore, the initial investment set by the minimum installed capacity required can also be reduced. More interestingly, from this table, the hub efficiency over time remains almost invariable, regardless of this delay, provided that the partial load optimization is achieved by using the sawtooth profile. So we got some conclusions. Even at tenfold lower CO2 emissions, advanced power generation systems in offshore petroleum platforms may provide higher overall performances than existing simple cycle gas turbines configurations. Still, the initial investment costs remain the main drawback of more environmental friendly setups, difficult to circumvent without the cooperation of societal and economic sectors, also aggravated by the lack of carbon taxation scenarios. A subsequent study that is going to be presented in a coming conference deals with the impact of the carbon taxation and the massification of the CCS units at commercial scale, so that more profitable configurations with lower environmental impact and initial investments can be envisaged. The delay of entrance in operation may also help mitigating the initial investment cost. Finally, we would like to acknowledge our funding partners Petrobras, CNPK, and Conscientious. Thanks for your attention.